Hi, my name is Benjamin. I've been working a bit on some low-level stuff. Namely, you might know that NCG has two register allocators, a linear scan allocator, which is the default, and a graph coloring one, which is sort of defunct, if you will. And a blog post by Andreas Klebinger kind of made me aware of that, which started me out on first trying to improve it, and then I fell down a rabbit hole and wrote a whole new allocator, which is a terrible idea. Anyway, so register allocation normally happens after destruction of single static assignment static single assignment form. However, like roughly around 2005, there was a flurry of research that started where they found certain interesting properties of interference graphs of SSA-based programs still in SSA form. And long story short, one of the nice properties is that it allows us to decouple the separate phases of the allocation. So we can now have our spill phase that just handles spilling, and then the coloring phase afterwards will just sort of work out without more spills. As opposed to the classic graph coloring one we see up top, where you kind of have to, so it's a heuristic, so we go in a loop, and while coloring fails, then we kind of have to spill something and we try again. I also dislike this because it kind of treats spilling like such an afterthought, where it's kind of really important for performance because memory access is so more expensive, of course. So design I settled on is based on two papers out of Karlsruhe University. And basically, there's a separate spilling phase, and then the coloring and coalescing, which is supposed to get rid of copies, etc. That's all wrapped into one for speed. Yes, of course, well, benchmarked it. I'm just going to go straight to results. Benchmarked it with no fib, which you all know. I've excluded a few benchmarks, which have some problems that are short running times, are a bit, unstable. But yes, just for the labels, I'm sure you can guess what linear graph and SSA mean. But there's one that's called Chitin, is where I took the graph coloring allocator, and I ran a sort of a renumbering phase before it based on SSA, because NCG emits some disjoint life ranges with the same virtual register name, which then it has to assign them to the same physical register and over constrains them and sort of, poses a problem. And I've also used the classic cost heuristic. So this is static Spellcode counts, which is not a perfect predictor of performance, but it's basically how many load and store instructions were inserted. We can see actually that the Chitin variant does work better than the standard graph one, and the SSA one in terms of static spill counts is close to linear. While I said it's not a great predictor of performance, honestly the overall trend is kind of there. Yes. I'm going to skip the copies and go straight to performance, so runtime results. And I don't know if you can read it, but the last 3 bars, that's the overall performance as compared to linear scan. So unfortunately, in the end, my allocator produces code that's like 0.5% slower. And yes, even the Chitin variant doesn't fix FRX graph, which I didn't expect it to be fixed so easily. There's some of these results I want to go into detail. For example, the Shootout category was kind of weird. Sort of why the graph color allocator performs so terribly. This one benchmark where it shows this more than 60% or almost 60% slowdown. And I've assumed because it spills in a loop, and well, that's just the way it is. And then I checked results for this Chitin variant, which does not spill at all. And so there's something strange going on there. I've looked at this week briefly, and I can't fully explain it, but well, there's something interesting going on there anyway. This is just a scatter plot of the SSA-based allocators benchmarks. We see a few outliers that I kind of maybe give me a hint on what's happening, what could be improved also in the other allocators. The almost 25% slowdown of imaginary Kahan is actually really interesting because it sort of compiles down to this one loop where it spends 99% of its runtime, and it just has to spill because there's a C call. And both my allocator and linear scan spill the same amount, and yet mine is 25% slower. And Andreas Klebinger helped me a bit to figure this out, and it just happens to be that these life ranges participate in the critical path of the loop, and it sort of reduces the overall throughput of the loop because there's one more instruction there. And then I checked why the linear scan allocator spilled this one life range that did not have that impact, and it's kind of pure chance. The linear scan just spills the next one, and I think they're sorted by unique, which kind of was a bit discouraging. Like, it beat me by chance, but it gave me a few ideas on whether we can use this as a metric in a scanner, whether we can give linear scan a different heuristic for spilling that might overall improve its performance. And I also figured out that actually some of the spills that happen in the loop could be hoisted out of the loop because they're invariant. And I experimented with some ad hoc improvements, but they fixed this benchmark and made others worse. So still work to do. And I also figured out that this call, we can actually get rid of this, but that's another story. It's another project. Some takeaways. I think there's still a lot of stuff to do. I think my algo could be improved, but I don't know if it's worth it. At least there's some way that I can experiment with different phases, and some other things that I would like to try out with the other allocators and CodeGen in general. There's a ticket which I want to update. I will probably do it tomorrow with the current state of things if you're interested. All right, thank you.